Okay, we're still working on 7.7. Now we're going to talk about the midpoint rule approximation. So we're going to review this actually because we've actually kind of seen it already. It was another equivalent way of obtaining the definition of the Riemann integral. But we're going to investigate it now as an approximation properly and investigate how it improves upon our previous methods, the left and right endpoint approximations. So let's first talk about our motivation. Why would we want to do this? Okay, so the left and right endpoint approximations are fast but crude. They're not really that accurate. You can already see that in the last video and the example that we chose. Even though we chose a fairly low value of n, we would need a significantly high number of subdivisions to obtain the accuracy that we really want. So, as we do in all of these techniques, we're going to suppose we really have to start with, we take a and b and we're going to subdivide it into these points x sub I, okay? But here, rather than taking an endpoint, which is likely going to be very different from the rest of the function values in each subinterval, we're going to take a midpoint. So let x sub I be a partition of a sub b with each x sub I is going to be derived from a, okay, where we get them each equally spaced apart. So the first one is a, the next one is a plus delta x, the next one is a plus 2 delta x, and that'll give us equal spacing between all of them, where delta x is going to be b minus a over n. So for each I then, we will construct the midpoint x sub I bar. The midpoint is the arithmetic mean of the two points. So it's going to be 1/2 times x sub I minus 1 plus x sub I. And we hope that this is more accurate. So we'll see. I'm going to draw the picture here. And so I'm going to illustrate what this looks like. And again, you can skip ahead a little bit so that you're not just watching me draw. But the idea here is x1, x2, x3, x4. That should be enough. Okay, so I'm going to draw again some curve that I hope is going to be, okay, there we go. So this time what we're going to do is we're going to find the midpoints. So here's x sub 1 bar, which is the midpoint of x sub 1 and a. And then x sub 2 bar, x sub 3 bar. It's literally the number directly in the middle of each subinterval that we've created. So there should be one for each subinterval, okay? So remember that our subintervals, if we trace them up to the function, right, they're telling us that we're going to approximate for each subinterval. The area underneath the curve in each subinterval now is going to be replaced with, we'll find the function value at the midpoint, and that's going to determine the height of the bar. And the area underneath each bar becomes the estimate of the integral. So it sounds bizarre, but bear with me, right? So in this case now, we should have both overestimate and underestimate on either side, because if we're approximating using the midpoints, that means we're looking for a function value that probably, most likely, is going to be in the middle of these values. So what I'm shading now is the error this time. You'll notice that the error proportionately is not so great. So to really think about this, right? First of all, is this going to give us the right technique, right? Is this actually going to approximate the area? So let's actually get into the approximation, because we've seen it through a picture, but we should formulate it formally. So we're going to fix the number of subdivisions n, and the midpoint rule approximation is going to be denoted capital M sub n is equal to the sum from I equals 1 to n of the function values at the midpoints times delta x. Okay, and then the limit as n goes to infinity, m sub n. Remember, we saw this in chapter 5. This should still give us the actual integral that we're seeking. So in the limit, this does converge to the integral, okay, as we saw in chapter 5. So how does this work? Okay, by continuity of f, which is an assumption that we're going to assume here, f sub x sub I is a good approximation to f of x values in a neighborhood. So in some interval near x sub I bar. So the approximation as a whole does pretty well, because I sub I bar is the middle of the subinterval, and so that neighborhood is going to look pretty close to. So if I can zoom in here on just one subinterval, I'll show you what that looks like. No, that's not what I wanted. Here we go. Just one subinterval, okay. Here is my midpoint, x sub I bar. Here's my function value, right? And by continuity, right, give a little bit of wiggle room around x sub I. And those function values shouldn't be too drastically different from f of x sub I bar, right? So then, that means if we replace, what we're really doing is we're approximating. If we think about what this is really doing, it's approximating f with the constant slope y equals f of x sub I bar.